Right now, as you are watching this, a spacecraft the size of a small car is hurtling through the void between the stars at 38,000 miles per hour. It is over 25 billion kilometers from Earth. The signal it sends home is so faint that by the time it reaches NASA's antennas, it carries less power than 100 billionth of 1 billionth of a watt. Your phone's Wi-Fi signal is roughly 100 billion times stronger, and it drops out when you walk to the kitchen. That spacecraft is Voyager 1. It launched in 1977 with 69 kilobytes of computing memory, which is less than a single photo on your phone. It runs on an 8-track tape recorder and processors that make a 1980s calculator look like a supercomputer, and it is still talking to us every single day. But Voyager 1 is dying. Its plutonium power supply is fading by about 4 watts every year. Its instruments are being shut off one by one to squeeze out a few more years of life. Within the next decade, it will send its last signal and go silent forever. What happens after that? What it means that this little machine will keep drifting through the galaxy for 1 trillion years, carrying a golden record with Bach and whale songs and a woman's brainwaves on it, that is the part of this story that will stay with you. Cape Canaveral, Florida, September 5th, 1977. A Titan IIIe rocket sits on Launch Complex 41, carrying a spacecraft that almost nobody outside of NASA's Jet Propulsion Laboratory in Pasadena is paying much attention to. The mission is called Mariner Jupiter-Saturn, which is about as exciting as it sounds. It had originally been part of a much grander plan, a 4-spacecraft grand tour of all the outer planets, designed to exploit a rare alignment of Jupiter, Saturn, Uranus, and Neptune that only happens once every 176 years. An aerospace engineer named Gary Flandreau at JPL had identified this alignment back in 1964. Congress looked at the price tag and killed the Grand Tour in 1971. NASA got funding for 2 cheaper probes instead. The engineers at JPL quietly built them tough enough to go much further than anyone was officially promising. At 12:56 UTC, the Titan rocket ignites. Almost immediately, something goes wrong. The second stage engine shuts down early, leaving 540 kilograms of propellant unburned. The Centaur upper stage has to compensate with an extended burn. When that engine finally cuts off, it is 3.4 seconds from running completely dry. 3.4 seconds. That is the margin on which this entire story exists. Everything Voyager 1 has done, everything it has discovered, every image it has sent back, every mile it has traveled into interstellar space, all of it rests on 3.5 seconds of fuel in a rocket stage that almost didn't have enough. And somehow, it gets worse, or rather, it gets unbelievably better. Voyager 1 reaches Jupiter on March 5, 1979, screaming past the giant planet at a distance of 348,000 kilometers. Over the next 4 months, it sends back roughly 18,000 photographs of the Jovian system, and nearly every single one of them contains something nobody predicted. It reveals Jupiter's Great Red Spot as a counterclockwise storm 3 times the size of Earth, with wind speeds exceeding 400 miles per hour. It discovers a faint ring around the planet that nobody knew existed. It finds 2 new moons, Thebe and Metis. The images of Jupiter's swirling cloud bands were so detailed, so violently beautiful, that scientists at JPL reportedly broke into applause when the first close-ups came through on the monitors. But the discovery that changed everything happened 3 days after closest approach, and it came from the most unlikely source. A 24-year-old navigation engineer named Linda Morabito at JPL was processing a long-exposure image of Jupiter's moon Io. The image was taken for navigation purposes, not science. She was looking at the edge of Io's disk to chart its position when she noticed something strange. A crescent-shaped cloud, 270 kilometers tall, was rising off the surface of Io and arching out into space. She had just found the first active volcano ever observed beyond Earth, And not just one. Voyager 1 ultimately identified 9 erupting volcanoes on Io, with plumes reaching over 300 kilometers above the surface. The entire moon was being turned inside out by volcanic activity on a scale that made Mount St. Helens look like a campfire. And here is the part that is almost too perfect to believe. Just 3 days before the flyby, 3 scientists named Peale, Casson, and Reynolds had published a paper predicting that tidal forces from Jupiter could melt Io's interior. Voyager confirmed their prediction within days of publication. That is one of those coincidences in science that makes you wonder if the universe has a sense of timing. Meanwhile, Europa revealed something even more tantalizing. An ice-covered surface laced with dark cracks and almost zero impact craters, suggesting something underneath was constantly resurfacing the moon. The implication was staggering. There might be a liquid ocean beneath that ice. Later missions confirmed it. At Saturn, Voyager 1 arrived on November 12, 1980, and found a system even stranger than Jupiter. Saturn's rings, which had looked like smooth, elegant bands through even the best ground-based telescopes, turned out to be staggeringly complex up close. Voyager discovered 5 new moons, found braided ring structures that defied simple physics, ghostly rotating spokes that appeared and disappeared like phantoms, and detected tiny shepherd moons physically maintaining ring boundaries like cosmic border guards. The close-up images of the ring system were so detailed, they immediately rewrote every textbook on planetary science. But NASA cared more about one specific moon than anything else in the Saturnian system. Titan. The only moon in the entire solar system known to have a thick, substantial atmosphere. NASA considered Titan so important that they designed Voyager 1's entire trajectory around the optimal Titan flyby. Every other scientific objective was secondary. The spacecraft passed within 6,490 kilometers of Titan's surface and found a world completely hidden beneath opaque orange haze, an atmosphere that is 90% nitrogen, surface pressure 60% greater than Earth's, and temperatures of negative 180 degrees Celsius. Scientists speculated about methane rain and hydrocarbon lakes pooling on the surface. Decades later, the Cassini-Huygens mission dropped a probe through that haze and proved them right. This choice came at a steep cost. The Titan flyby trajectory flung Voyager 1 below Saturn's south pole and out of the ecliptic plane at a 35-degree angle. There would be no visit to Uranus, no visit to Neptune. That privilege went to Voyager 2, which would go on to be the only spacecraft to ever visit those ice giants. Voyager 1 had served the planets well. From this point forward, it was heading for the stars, and it was carrying something extraordinary with it. If you've been enjoying this deep dive into Voyager's story, hit subscribe. We cover space, science, and the stories behind humanity's wildest achievements every week. All right, so here's where this story goes from incredible engineering to something genuinely human. Bolted to the side of Voyager 1 is a 12-inch gold-plated copper phonograph record designed to survive 1 billion years in the vacuum of space. Its aluminum cover is electroplated with ultra-pure uranium-238, which has a half-life of 4.468 billion years. So any future finder could calculate exactly how old the record is by measuring the radioactive decay. Diagrams on the cover show how to play it, how to decode the images, and a pulsar map pinpointing Earth's location relative to 14 pulsars. Hand-etched into the record's run-out groove are the words, "To the makers of music, all worlds, all times." The record was assembled by a 6-person committee chaired by astronomer Carl Sagan of Cornell University. Andrew Yan served as creative director. Frank Drake, the astronomer behind the Drake equation, was technical director and designed the pulsar map. Timothy Ferris produced the record. John Lomberg handled the design. Linda Salzman Sagan organized the greetings. They had roughly 6 weeks and a budget of $18,000 to distill all of human civilization onto a single disc. Think about that for a second. 6 weeks to decide what matters most about your entire species. The record contains 27 musical selections spanning 90 minutes. Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, Mozart's Queen of the Night aria, Chuck Berry's Johnny B. Goode, Louis Armstrong playing Melancholy Blues, Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a 2,500-year-old Chinese Guqin piece called Flowing Streams, Georgian choral music, Navajo night chants, Peruvian pan pipes, Javanese gamelan, Aboriginal Australian songs. When ethnomusicologist Alan Lomax complained that rock and roll was adolescent, Sagan pointed out that there were a lot of adolescents on the planet. Beyond the music, the record carries 116 images encoded in analog format, including DNA structure, human anatomy, landscapes from around the world, and a page from Isaac Newton's Principia Mathematica. There are greetings in 55 languages, from ancient Sumerian to Mandarin Chinese, and one from 6-year-old Nick Sagan saying hello from the children of planet Earth. A 12-minute sound essay captures thunder, bird song, whale songs, a kiss, a mother's first words to her newborn, and a Morse code message reading per aspera ad astra, through hardships to the stars. But the extraordinary item on the entire record is 1 minute of compressed brainwaves belonging to Anne Druyan. She recorded them at Bellevue Hospital in New York City while meditating on the history of Earth, on the beauty and the violence of civilization, and in her final moments of recording, on the wonder of falling in love. 2 days earlier, she and Carl Sagan had confessed their love to each other during a phone call about which Chinese music to include on the record. They married in 1981 and were together until his death in 1996. As artist Dario Robleto once observed, her heart is the only human heart that has actually exited our solar system. And that detail, more than any of the science or engineering, is what makes Voyager 1 unlike anything else humanity has ever created. It is not just a machine, it is a love letter, sealed inside a bottle, thrown into an ocean so vast that the odds of anyone finding it are essentially zero. And they threw it anyway. Now, the sun does not just sit quietly in space, it constantly blasts out a stream of charged particles called the solar wind, which inflates an enormous protective bubble around the entire solar system, known as the heliosphere. Think of it like a force field. Everything inside that bubble is the sun's domain. Everything outside it is interstellar space, the ocean between the stars, a place where no human-made object had ever been. On December 16, 2004, at 94 astronomical units from the Sun, Voyager 1 hit what scientists call the termination shock, the boundary where the solar wind abruptly slows from supersonic to subsonic speeds. Imagine standing in a river where the rushing water suddenly pools into a calm lake. That is what Voyager flew through. It then spent 8 years crossing the turbulent Helios Heath, the compressed region between the shock and the heliosphere's outer edge. And then, on August 25, 2012, at a distance of 121.6 astronomical units from the Sun, about 18 billion kilometers, Voyager 1 crossed the heliopause and became the first human-made object to enter interstellar space. And nobody knew it had happened. Not at first, not for over a year. Here is the detail that everyone missed. Voyager's plasma spectrometer had died back in 1980. The one instrument that could have directly confirmed the crossing was not working, so NASA had to wait for an indirect measurement. In March 2012, a coronal mass ejection blasted away from the Sun. 13 months later, it finally reached Voyager's location and caused the surrounding plasma to vibrate. Voyager's plasma wave subsystem detected oscillations corresponding to an electron density 40 times higher than inside the heliosphere. That matched the theoretical prediction for interstellar space. Meanwhile, charged solar particles dropped 1,000-fold, and galactic cosmic rays surged 9%. NASA finally announced the crossing on September 12, 2013, more than a year after it happened. Ed Stone, the mission's project scientist, declared it mankind's historic leap into interstellar space. But interstellar space is not empty. It is filled with cold, sparse plasma thrown out by ancient supernova explosions, threaded with magnetic fields, and bombarded by high-energy cosmic rays from across the galaxy. From 2017 onward, Voyager detected a persistent faint hum of plasma waves, enabling near-continuous density measurements. The density kept rising, revealing that the space between the stars gets thicker the farther you travel from the sun's protective influence. And despite crossing into interstellar space, Voyager 1 has not left the solar system, not even close. It will take roughly 300 years just to reach the inner edge of the Oort cloud, the vast shell of icy bodies that extends out to about 100,000 astronomical units. Passing through the Oort cloud entirely takes about 30,000 years. In November 2023, Voyager 1's flight data subsystem, a 16-bit computer running on 69.63 kilobytes of memory, started transmitting gibberish. Instead of usable science and engineering data, it sent an indecipherable repeating pattern of ones and zeros. The spacecraft was receiving commands fine. It was operating normally. Its instruments were collecting data. But Earth could not read a single thing it was sending back. It was like getting a phone call from someone 15 billion miles away and hearing nothing but static. For 5 months, Voyager 1 was effectively mute. The team at JPL had to diagnose and fix a computer built in the mid-1970s from a distance where every command takes 45 hours to send and receive a response. In March 2024, engineers sent what they called a poke command, prompting the computer to dump its entire memory contents back to Earth. When the data finally arrived, the diagnosis was almost absurdly small. A single memory chip had failed, corrupting roughly 3% of the onboard memory. One stuck bit, likely from a cosmic ray strike or simple wear after 46 years exposed to the radiation of deep space, had rendered a critical 256-bit chunk of flight software unreadable. The chip could not be repaired, so the engineers had to get creative. They needed to relocate the corrupted code, but no single block of empty memory was large enough to hold it. Their solution was to split the code into fragments and scatter them across multiple memory locations, then update every cross-reference so the pieces still work together. On April 18, 2024, the software patch was transmitted, beginning its 22.5-hour journey across 15 billion miles of space. On April 20th, the first coherent data in 5 months arrived at JPL. By June, all 4 science instruments were reporting again. Then in October 2024, a routine command to turn on a heater triggered Voyager's fault protection system, which shut down the main X-band transmitter entirely and switched to a backup S-band transmitter that had not been used since 1981. Engineers at the Jet Propulsion Laboratory were not even sure they could detect an S-band signal from 15 billion miles away. They could. By late November, the X-band transmitter was back online and regular operations resumed. But the incident exposed just how thin Voyager's margins have become. A single heater was enough to trigger an emergency shutdown. In February 2025, NASA permanently switched off Voyager 1's cosmic ray subsystem to conserve power. Voyager project manager Suzanne Dodd was direct about the situation. If they did not start shutting down instruments now, the entire mission would have only months of power left. The low-energy charged particle instrument is scheduled to go next. That will leave just 2 active instruments aboard, the magnetometer and the plasma wave subsystem, listening to the faint hum of interstellar space. The team keeping Voyager alive works from an off-campus facility at the Jet Propulsion Laboratory called Woodbury, where vintage computer workstations that can still interface with 1977-era flight software are carefully maintained. The team numbers about 14 people now, down from hundreds during the planetary encounters. They program in assembly language and Fortran, translating commands from modern Mac laptops into formats the spacecraft's ancient 18-bit and 16-bit processors can understand. The ground computers that originally processed Voyager's camera images no longer exist anywhere on Earth. The camera software was deleted from the spacecraft years ago to free up memory. Even if they wanted to take one more picture, they could not. Voyager communicates through NASA's Deep Space Network, 3 ground stations positioned 120 degrees apart in longitude so that at least one is always facing the sky as Earth rotates. The stations sit in Goldstone, California, near Madrid in Spain, and outside Canberra in Australia, each one built around a massive 70-meter dish antenna. Those dishes were originally 64 meters wide, but NASA expanded them specifically to support Voyager 2's Neptune encounter in 1989. The signal that reaches those enormous antennas from Voyager 1 carries the power of roughly 10 to the negative 20th watts. Data trickles in at 160 bits per second, about 4,500 times slower than a dial-up modem from the 90s. During the Jupiter encounter, data flowed at 115,000 bits per second, 720 times faster than what they get today. Every year, as Voyager moves farther away, the whisper gets a little quieter. Dr. Edward Stone served as Voyager's project scientist for 50 years, from 1972 until 2022, the longest tenure in NASA history. He passed away on June 9, 2024, at the age of 88. He once said that nature is much more inventive than our imagination, and that the journey of a lifetime was still not over. His successor, Linda Spilker, who has worked on Voyager since 1977, put the mission's fragility simply. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be the last. Voyager 1's power comes from 3 radioisotope thermoelectric generators containing plutonium-238, which has a half-life of 87.7 years. At launch, those generators produced 470 watts of electrical power. Today they produce roughly 200, and that number drops by about 4 watts every year as the plutonium decays and the thermocouples degrade. Engineers expect at least one science instrument to operate into the early 2030s. Basic engineering telemetry might continue until around 2036, when the RTG unit simply can no longer produce enough electricity to power the transmitter and keep the spacecraft's electronics from freezing. After that, Voyager 1 goes quiet, but it does not stop. Nothing out there will slow it down. The spacecraft is heading toward the constellation Ophiuchus, traveling at roughly 3.5 astronomical units per year, about 17 kilometers every second, covering 1 light year every 18,000 years. In approximately 40,000 years, it will pass within 1.6 light years of a dim red dwarf star called Gliese 445 in the constellation Camelopardalis. It was not aimed at this star. That is simply where the combined gravity assists from Jupiter and Saturn sent it nearly 50 years ago. It will never leave the Milky Way. It does not have the speed to escape the galaxy's gravity. NASA once put it simply: the Voyagers are destined, perhaps eternally, to wander the Milky Way. The estimated timescale for Voyager to collide with a star is 10 to the 20th power years, 100 quintillion years. That is 7 billion times longer than the current age of the universe. The spacecraft structure will endure essentially indefinitely in the vacuum of space. One analysis estimates the Voyagers could exist in recognizable form for more than 1 trillion years. On February 14, 1990, Valentine's Day, from a distance of 3.7 billion miles, Voyager 1 turned its camera back toward Earth one last time and took a photograph. Carl Sagan had spent years lobbying NASA for this image. Many at the agency thought it was pointless, scientifically worthless, a waste of the spacecraft's dwindling power. Sagan insisted. He wanted humanity to see itself from the edge of the solar system. In the image, Earth appears as a tiny speck, just 0.12 pixels wide, caught in a scattered band of sunlight caused by the camera's optics. Everything you have ever known, every person who ever lived, every war that was ever fought, every love story, every act of kindness and cruelty happened on that pale blue dot. Sagan reflected that it is our responsibility to deal more kindly with one another and to cherish the only home we have ever known. Voyager's cameras were permanently shut down shortly after the photograph was taken. There was no more reason to look back. Right now, Voyager 1 is approaching a milestone that will arrive this year. Sometime in 2026, it will cross 1 full light day from Earth, meaning a message sent from NASA will take 24 hours to arrive, and the reply will take another 24 hours to come back. A full 2-day round-trip conversation with a machine built before the first Star Wars sequel, before the internet, before most of the people watching this video were born. Somewhere in the dark between the stars, long after our sun has expanded into a red giant and consumed the inner planets, a small spacecraft will still be drifting. Its transmitter will have gone silent decades earlier, its instruments long dead, its mission over in every technical sense. but it will still be carrying a golden record with Bach and Chuck Berry, thunder and whale songs, a mother whispering to her newborn, the brainwaves of a woman falling in love, and a photograph of a pale blue dot that no longer exists. The odds of anyone ever finding it are vanishingly small. Space is mostly nothing. Trillions of years of empty vacuum between the stars. But Carl Sagan understood that the record's true audience was always us. It forced a small group of humans to sit down and decide what mattered most about their species. And with 6 weeks and $18,000, they chose music, science, laughter, and love. They did not include war. They did not include hatred. They sent what they wished we were, and in doing so, maybe showed what we could be. Voyager. One will outlast every building standing, every nation currently drawn on a map, and eventually the Earth itself. A trillion years from now, long after the last star in the Milky Way has burned out, a small spacecraft will still be out there, carrying a message that says we were here, we were curious, and we reached. If you want to go deeper into the stories of what humanity has sent into the cosmos, check out this video right here.